Welcome to CE Rocketry. Today we're going to be doing our first overview video of our motor program.
So we've developed 7 motors so far, and we've been able to successfully fire all of them, and each one is building off advancements and failures that we've learned from in the past.
A lot of failures. As we mentioned in our project overview video, the motors that we made are based off of King of Random's video on how to make solid rocket motors, and essentially they use a combination of powdered sugar and stump remover, which is potassium nitrate, in order or for the solid fuel. This is M1, our first motor. This one, it burned successfully for a little bit, but eventually the top cap that keeps a good throat pressure inside the motor exploded out. In the cap, there's a hole drilled out that basically controls the rate of burn. And essentially, the expanding gas coming outside of the motor was the same pressure as, or a similar pressure to the atmospheric pressure, which basically resulted in a loss of thrust. To put it to put it simpler, it was just a fire inside of a tube.
So this is M2, the second motor we built, and if you notice, it's a lot shorter. This one's only, I think, 3 inches, whereas our first one was 5 inches, and that's mostly because our drill bits aren't long enough to drill through, because you have to drill a bore through the middle of the motor, down to the rear cap, so that the solid fuel burns evenly across it. Otherwise, you kind of have some wacky thrust. But yeah, so we made this one smaller so that it would hopefully burn more evenly. And this one actually worked. The top cap stayed on. So yeah, this was our first mostly successful motor.
This is M30. This was our first motor that we attached an external nozzle to. The nozzles are 3D printed and then coated with a heat-resistant paint on the inside. Even with the heat-resistant paint, there's still a bit of material loss just because of the extreme heat inside the motor. But it's not so much so that we lose the nozzle's effectiveness, so it's more of an ablative type effect. In this motor, we just kind of duct taped the nozzle on. This was mostly because we were just trying to see if the nozzle would hold up to any sort of heat at all from the motor. So after a little bit, we did lose the nozzle during the middle of the test. So from inspection, we looked at the nozzle and found that it held up well to the small amount of heat that it was exposed to, and so we decided that we could start doing tests with the nozzle exposed to the full heat of the motor.
So this is M4, and it's the first one where we actually epoxied the nozzle onto, and as you can see, it held up a lot better. The nozzle is still attached, except that we did lose the end cap, and we kind of assume that that's because this nozzle is, maximizing the pressure a lot more than just the clay was. So then our end cap wasn't strong enough, and it blew out, and it was a big smoky ball.
Basically, the pressure that the nozzle was creating because of the backlog of expanding gases was greater than what the end cap could keep, and so instead of just forcing more gas out the back of the nozzle to keep the pressure down, it ended up just blowing the cap out, and so we basically had to, on the next revision, make sure we kept the end cap bigger to withstand the higher pressures of a nozzled engine. We're moving on now to M6. We skipped M5, but that is for reasons that we will explain later. This was our first successful burn with the nozzle. You can see in the video now it burned it was less than 3 seconds, and you could tell just by watching it launch and from the camera that it seemed more powerful than just the non-nozzled engine. We don't have any scientific way of doing that yet. We're working on it, and that's something we'll explain later in the video. But just from observation, we can see that these engines are producing more thrust.
Alright, so this is M7, and it's basically identical to M6, and it was almost the same in performance as well. As we said, we don't really have a scientific way of measuring it yet, so there wasn't anything we really observed that was different, but we did try on this one we drilled a smaller bore through it. And also on M6 and 7, the nozzle is a bit bigger, like around, the collar kind of thing here. So this one actually like slides over as opposed to our earlier ones where it was just kind of epoxied on the top. So yeah, that's also a difference.
So M5. M5 was difficult because for these later nozzle motor variants, we didn't include the top cap of clay like what is on M1 and M2. They're necessary for M1 and M2 because they don't have coverings on top. Without that cap, the motor, like I said, would just burn at atmospheric pressure, which is not what we want. However, with a nozzle motor, we don't need that top cap because the nozzle is what's producing that pressure and that throat pressure. However, for M5, we put that top cap on anyways, without thinking, and that ended up making it so the powder was too far below the top of the nozzle for our electronic lighter to ignite. So we had no way to ignite it. Eventually, 4th of July rolled around, we were able to buy some fuse from a fireworks stand, and we lit it using that. However, the bottom cap shot out, and because of I don't even know how to explain what happened. You're probably watching it right now, but basically the whole test stand just started spinning. Yeah, it was interesting to watch, but we were just happy to not have a loaded motor sitting around.
So for the future of our homemade rocket engines, the first thing we want to do is create an actual ejection charge, because right now if you launch this in a model rocket, it would go up, but it would come back down at a very high rate of speed because there's no way for the parachute to deploy. So we want to make an ejection charge, and to do that we need some black powder, which we are still trying to obtain right now.
So we talked earlier about how we are working on a scientific way to measure the thrust difference between a non-nozzled motor like M1 and M2 to a nozzled one. So basically we're going to make a test stand that takes use of a Newton gauge to measure the force output. It'll be pretty simple to do. It's basically, that's like a a spring gauge like we use at our any college or high school lab. We're going to have a way of, kind of like a slider stand, a way of to hooking up the engines and testing the thrust output from each. So right now we need to order that string gauge, and then we're going to make the test stand out of PVC.
So all of these motors we've fired so far are with 1/2-inch PVC, but if those all go successful, like with our rocket launches too, then we're going to try to make a 2-inch version, which I don't really know if we'll actually have like a rocket to launch with it, but
It's kind of big.
It'll just be something, that'll hopefully like give out a lot of thrust and just be a good experiment and something cool to see.
So 2 inches is kind of a large size to make a solid rocket motor out of. We might go down to 1.5 inches or something, but basically the reason we want to do this is because we want to make a hybrid rocket engine in the future. So for solid rocket motors like the ones we're developing, both the fuel and the oxidizer are in solid form. For these motors we had potassium nitrate as our oxidizer and powdered sugar as the fuel. However, in a hybrid rocket engine, the fuel is on its own inside the motor, and there's some kind of external source of either liquid or gaseous oxygen. So by moving to a larger motor size, we're able to start using and utilizing hybrid rocket fuel technologies. And we don't think we're going to launch a hybrid rocket engine, but we would like to develop one on a test bed.
So that's it for this video, but make sure you stay tuned because in the next video we'll be talking about Double Fillet, our test rocket for our homemade engines.